So the first thing to do, and I'm going to bring up my File Explorer so that I can show you what I am doing. This file here, our workshop01.rdata, is an R environment that I've already produced for you. And to launch R, you can either double click it and launch it if that's how you have things set up. If you have RStudio set up, it might launch RStudio for you, but you can always right click on it and then choose to open with. And if R GUI doesn't show up in here, you can go down to choose another app and navigate to the location where R is installed and choose the rgui.exe program, and it will launch exactly what you have visible here in my current viewer. So it will load the R console, and we'll end up down here with a small sort of greater than symbol. That is the prompt. That's where we're waiting for the next function to be entered. If you have that, you can look at the very first row. It tells you what version of R you're running. They give them all interesting names, but it makes sure that you are always running the latest version of R. The next most important thing is to know where you are working, and that's called the workspace, because you can launch R from one location but have your workspace somewhere else, and all of a sudden you don't know where your files were stored when the day is done. So generally, when you launch R by double-clicking on the file, that R data file that I gave you, the workspace should end up being where you launched that file from. However, there are sometimes ways by which that doesn't happen. It's a nice way to check what workspace we're in, and we can type in the function get working directory, get WD, and this is a function, and after any function in R, we have to provide an open and closed curved bracket, and when we hit enter, it will provide us the path to where we currently launched that file from. So for me, on my computer, my desktop has a folder on it which I called our Workshop 01. My files are in there. I launched from there. That's where my working directory is going to be located. Your computer obviously, well, most obviously doesn't have a folder on it that's called Tarmo-research, so it will look different than mine, but it will tell you where you've launched your work from. That's the folder in which everything that you do is going to be saved. When you try to read files in, write files out, they're going to be written to that working directory. It's good to know where that is, because sometimes you're working on multiple different projects and you might have multiple different working directories, one for each project. It helps you keep clear where your files are located so that you don't overwrite things, because we often use similar kinds of names in different projects, and that way we don't run into those kinds of problems. Okay. Couple of key points to start off with. If we're in the right workspace or the working directory, we know where we are, we need to understand some of the key things about R. The first thing is that it's case sensitive. That means Tarmo with a capital T and Tarmo with a lowercase t mean different things. So if you name a variable in one way, with capitals or no capitals, you have to make sure that you always refer to it in that way, because capitalization really does matter. And a couple of really good sort of rules of thumb: never start naming a variable with a number, and don't put characters that are sort of operators and things into file names or into object names, because they end up getting sort of really confused with how you call them, because it will think that they're operators. Okay. That said, everything that we do in R inside this workspace that we've currently got open is to produce objects. So anything that we want to store, anything that we produce, any calculations that we run and want to record the result of, are stored as what we call objects. And we often want to know what objects currently exist in our workspace. And the very quick way to get that information is to call what's called the list function. And in R, list is simply ls. And again, it has these curved brackets because it's a function. We'll talk about what these curved brackets are for in just a moment. But when we call the list function and hit enter, it returns something that looks very computer science-y to us. In this case, it says character 0, and this is the elegant way by which R tells us there's nothing in your workspace. Once we start creating content and creating objects, when we run this list function, it will give us a listing of everything that's stored in this environment. So thinking about these curved brackets then, what on earth are they for? Well, those curved brackets are where we can enter arguments or sort of parameters that control how a specific function is run. You say, well, how do I know what to put in there? Well, we can find this out in many different ways. One of the easier ways is to type in args and then put in the name of the function that we're interested in and close the curved brackets. So here's sort of a really meta way of demonstrating how this works, because what we're doing is we're putting the parameter ls, or the argument ls, into the function call for args, and this will return the arguments that are associated with the function list. So when we hit enter, it gives us a whole bunch of feedback. And it says here that ls is a function, but when we call ls, we could specify an argument for name, an argument for position, an environment for an argument for environment, an argument for all.names, an argument for pattern, and an argument for sorted. And there's all sorts of ways by which we can control how this list function works. So basically, and we're not going to go through every single one of these things, we could say, let's call the list function, but we can specify a pattern. So if we have a series of objects that, let's say, always have the first 4 characters consistently named, we can put in that pattern, and it might then pull up only those objects in the listing, so that instead of potentially returning hundreds or thousands of objects when we type in list, it will return only the ones that have a name with a certain pattern associated with it. We can also have list return objects from other working environments and so on. But those are things that are a little bit more advanced and things that might be used in a different level of this kind of R training workshop. But for any function, we can always use args, and then in curvy in these curved brackets, we can put in the name of the function, and it will tell us all of the things that we can set for that function call. We can also find this out in the help module, where if we run help and put in the name of whatever function we're interested in, and we hit enter, it won't show up here the way that I'm currently displaying it, but it will launch a web page, and it will feed all of the help information into it that pertains to the function that you're interested in, and it will tell you exactly what is it, what does it do, what are all of the arguments, what values can they set, what do the various settings do. It will give you examples of how to run that function. It often tells you who wrote that function and how you can contact them if you want to get into contact with them. Usually not for really simple functions such as list, but for functions that are much more sort of advanced, there's always an author that you can contact for information about it. So I'm just going to delete this line because I don't need it. The other thing that I don't have on my PDF, but something that might be of real use to you, is that to save typing commands that you may need to type often, if you simply hit the up and down arrow keys, you can recall function calls that you've already used. So if I hit the up arrow, notice that it'll just call or it'll rewrite onto my prompt the last function that I called. If I hit up again, it will go to ls. If I go up before that, it'll be the get working directory, and you can then just hit enter. You don't have to type the entire string of code again. And if you want, you can use the down arrow key and just cycle through them until you get back to the regular prompt. If you've got something on the prompt that you don't want there, you can use the backspace key and delete things. You can also hit escape and it will get rid of it. Notice that it just moves the prompt a little bit farther over. While that might look a little bit ugly, you can just hit enter and just get a nice clean prompt back again. So this is, again, not really learning how to use R. This is learning how to do things that make the environment more comfortable for you. Are we okay so far with sort of what R looks like? Okay. Let's create some objects. To create objects, we need to know of a very specific operator, and it's called the assignment operator. And the assignment operator is a glorified looking arrow. So I'm going to create an object, and I can create whatever name I want. I'm going to call it Fname, and then I'm going to use the less than and the hyphen sign together, and it looks like an arrow that's pointing left, and that's going to say take anything that I put on the right side of this arrow and move it in the direction that the arrow is pointing and write it to the object that I've just created or that I've named as Fname. And because my first name is Tarmo, I'm going to, in quotation marks, put my name. This tells the interpreter that this is a character string, that this is text, this is not numeric data or data of any other type. And it's going to take that and it's going to write it to an object called Fname. And when I hit enter, you're going to notice that nothing really exciting happened. I'm just going to change the size of this window a little bit so that we can see the bottom, because it seems to be getting cut off there. So when I hit it, nothing happens. And this is something to keep in mind. R doesn't really tell you that something worked. It doesn't always tell you that something didn't work. It doesn't tell you when you overwrite something. So you have to be careful and know what you're doing, because you can very easily overwrite work that may have taken several weeks of processing to produce. So you want to make sure that you're clear on what data you're taking and what object you're assigning it to, because if that object already exists and it has a tremendous wealth of information in it, it's simply going to overwrite it. It's not going to ask you, hey, do you want me to overwrite this object? All right, so now if we go back to our list function, ls, with the two curved brackets, and we hit enter, notice that now it doesn't say character 0. It says that we have an object called Fname. It's exactly the one that we just created right up here. So that's great. Let's create another object, because we can, and I'm going to call this Lname. Lname. I'm going to put the assignment operator, and I'm going to, in quotation marks, put my last name. And again, it doesn't tell you that it did anything, but we can always call the list function, and we can see that now there are two objects in this list, Fname and Lname. And you might be looking at this and saying, well, what does this 1 mean? This 1 in the square brackets is a simple way of trying to keep count of how many objects are in the result that's being shown on the screen. So it's a little bit tricky to get your mind maybe wrapped around this, but when we call list goes into our working environment and it figures out how many objects are there. It takes the names of each object and it attaches them as elements into a vector. So this vector then has some length. This vector happens to have a length of 2. There are 2 object names in it, but because when I write them on the screen here, and there are only two objects, it writes down the number of the first object that you see in this line. So Fname would be the first object in this vector of object names in this vector. Lname would be the second, but there is no third or fourth or fifth or sixth or seventh as we get down to the end of the screen. And if we have many objects in our working environment, let's say 30 or 100 or 200, it's going to require many lines of the screen to write them out. Then the next line, as everything wraps down, will have another number which gives the object number for the first one in that row, so that you can quickly figure out how many objects you have, or if you want to refer to those objects by a number, you can quickly figure out what that number is. So that number doesn't mean much, well, it's not very useful when there are very few objects, but when you get into a project and you have tens, hundreds, thousands, hundreds of thousands of objects, that number is really important because it helps you figure out where you are. Okay, so if what I just said was that ls returns an object that is a vector, then we should be able to figure out how many elements are in this vector, and we can do that using a function called length. But rather than just calling length, we have to tell it what to calculate the length of, so we need to provide an argument for length. And in this case, I'm just going to give it the vector that we get from ls. So just like in order of operation, when we're talking about bed mass, we do things in brackets first. So first, this function will resolve the listing of our workspace, and then that returns a vector. Now that vector is going to be the argument that is interpreted by this function called length. So when I do that, we see that the length of this vector is 2, and clearly there are 2 objects in the ls vector, which basically tells me that I have 2 objects in my workspace. So this is relatively easy. I mean, it's easy enough to do ls. You see that there are 2 objects, you're done. But again, when you have hundreds of objects and you need to know how many are there, then this is a really great way to get that information. Or if you want to produce later some sort of a loop that runs through each object and you need to know how many times I need to run this loop, you can then very quickly get this value that tells you how many objects are in the workspace. So it's simply taking simple functions, maybe nesting one in the other, just to make sure that it comes out nice and clean. We can look at this in a slightly longer fashion, but let's create an object that I'm going to call objects. And I'm going to write into this object, which I've called objects, the result of ls. So remember, ls as a function returns a vector. It's going to write that vector and store it as a new object in our workspace called objects. So I'm going to hit enter. If I type ls, we should now have 3 objects in our workspace. We have fname, lname, and objects. And like, oh, that's really great. We can look at what each of these objects actually stores by typing the name of the object. So let's just type fname. It's the name of the object. And when I do, we can see that it returns Tarmo, which was what I gave it up above right here. I could type in lname, and it gives me my last name. And I can type in objects, and it will tell me the 2 object names that are in my workspace. So remember that ls returns the names of the objects. By typing the name of the object, we get the contents of what that object or that variable is storing. So that's really great. We now have this object, which I call objects, we can pass that to the length function and calculate how long or how many elements are in this vector. And it also gives me 2. It's exactly the same thing as doing this. It's just that originally, when I did length of objects, I needed to have an object or an argument here called objects, which I created up here by taking the results of ls and storing them to objects, and then calling the length of objects. In this case here, I'm doing it all in one step. So I'm not creating an intermediate object that's actually stored in my workspace. It's resolving ls and sending that to length, and we end up with this same result. Obviously, now we have more because I've already produced this object in my workspace. So now there are 3. When I first ran it, there were 2. Are we okay so far? Hearing no complaints, let's continue on. The other thing that we often need to do when we're working with R, particularly if we come back to an environment that we haven't worked on in 5 minutes or 3 days or 6 months, and we need to remind ourselves, what are these objects? We often need to know what their structure is. So in R, there's a function called str, which is short for structure, and we can then provide the name of the object, and it tells us about it. So if I put in here the name or the object Fname, it tells me here that this is character data, which means it's text, so we know that it's something that we can't perform mathematics with. And if it's short, it simply tells me what the contents is. If it's a really large data set, it will just give me the first few elements of that data set, just so that we get an idea of what it looks like. Different types of data that are stored as objects will have different structures associated with them, and they can get relatively complex. But when we need to know how to operate or manipulate any object, knowing its structure allows us to say, yes, these are what the subparts of this structure are, and it reminds us how we can interact with them. If I look at the structure of objects, for example, it tells me that I've got data that's of character type, but in this case here, this is a vector that has 2 elements, and again, it just starts to list them for me. But if it was really long, it would cut it off and it would just say, this is what the first piece looks like. But it tells me that this object in my workspace, which I called objects, is a character vector, has 2 elements, and here we can see those 2 elements, Fname and Lname. So we have a way to get this information out of R and not having to memorize it in our heads. There's also a whole series of really useful little functions that in R help us to understand something about the objects that we've stored. And I'll look at some of them here today. Is.vector. And then we put in the name of an object. So it's asking the question, is this object in my workspace, which I call objects, is it a vector? And it will return either true or false. So sometimes you are trying to assess whether or not something is character, or is it numeric, or is it a vector, or is it a matrix, or is it some other data type. This very quickly tells you true or false, and then you know what you can do with that data. Instead of is.vector, we might say is.numeric, and it's not. And note that these Boolean operators, these things that resolve to being either true or false, will always have true in capital letters and false in capital letters. If you type them in lowercase, It doesn't see them as being Boolean operators. So they must always be assigned as being capital letters. So there's a whole series of these tests. Is.vector, is.numeric, is.matrix, is.character. Whole series of these things that you can then run to test whether or not that object is of a certain type. Because obviously, if something isn't numeric, you can't do math with it. If it isn't a matrix, there are certain calculation types that you can't run. So again, it allows you to test and ensure that you understand the format of your data. Okay? So with list, structure, and these is.vector, is.numeric, is.matrix, and so on, you can get a sense of what data objects do I have in my working directory, in my workspace, and what's in them, and what is the structure, and what type of data do I have. So really useful for sitting down, particularly when somebody else, let's say me, gives you a data set and you need to familiarize yourself with what's there. It allows you to do that relatively quickly. So now, the next thing that I'm going to do is I'm going to jump a little bit farther ahead. It's just going to allow us to ensure that we have consistency when we do a lot of this work. And that is because we're going to do some work with random numbers. And in computing, random numbers are not really random. I mean, they're random, but it's actually a long pre-created list of numbers. And as the computer needs a random number, it just takes them from that list in sequence. But they've been randomly generated. You just happen to not know what that sequence is, and you don't necessarily know where the computer starts selecting those random numbers from. And that's great, but if you want to replicate your work, it becomes a problem. So if you're wanting to be able to replicate work, what we can do is set what's called the random seed to a specific location, so that any time we come back and we run some code, it will always start the selection of random numbers from that specific location. And that means if each of us set the same random seed and we each do work with random numbers, we will actually each end up with identical results, which is great if you're teaching stats and you want to make sure that people got the right answers. But it also means that if I happen to accidentally delete my data and I need to get it back, I can always simulate it again with the same random seed, and I have sort of the ability to go back in time and basically save my ass, is what it comes down to. So what we're going to do is we're going to call a function called setSeed, and you can put in any integer here. I'm going to put in 100 just because I can, and that's basically telling the computer this is where we're going to start our random number sequence from. And if I do that, anything that I do that uses random numbers or any level of randomization, it's always going to be constant. And if you are working along and you type set.seed and you also specify 100 as the argument, and you call a random sequence, you'll see that your numbers are exactly the same ones that I've got. That's really, really useful. Okay, so that's great. We're going to come back to this concept in just a moment. First thing I'd like to do is create just a few more objects so that we have some things to work with in our environment. So what I'm going to do is I'm going to create an object called age, and I'm going to put in a number. And notice that this has no quotation marks because this is actually numeric data. It's not character data. Okay? So if I were to look at the structure of age, it now tells me, instead of CHR, it tells me that I've got numeric data, and this is a 47. So if I wanted to see what was stored in age, I can type in age, and I can do things like age times 2, and I can actually do math with that object. Okay, so the object name simply allows us to refer to the values that are stored inside that object. Now, it's not in the PDF, But if I created another object, and notice this one has a capital A, so it's different than the previous one, and if I did this, and I specified 47 in quotation marks, it's now going to look at that 47 as being character data and not numeric. So if I look at the structure of capital A, age, notice it says this is character data, and it puts it into quotation marks, so that if I do age times 2, it tells me you can't do it, because it can't multiply a character by a value. It just doesn't make any sense. So again, depending on how we create the objects, we control whether or not it's going to be character data or numeric data. Let's create a couple more things. I'm going to create a new object called grade. So I got 94.2 in a class. Yay me. Okay. We can again look at a listing of what we have. Now we have a lowercase age, uppercase age, Fname, grade, Lname, objects, and it sorts them in alphabetical order, not in the order in which you create them. Okay, we can add some more things here. Let's create an object called favorite numbers, and the arrow, again, the assignment statement is pointing to the left. This again is good computer programming style, where we always have the object that we're creating or that we're assigning to on the left side. The arrow points to the left, and then anything that's on the right hand side will be assigned to the object on the left. It does work the other way, where you can turn the arrow pointing to the right, but the entire world of computer scientists will basically give you that that's not good style. So let's always keep the assignment arrow pointing to the left. Let's always have the name of the object that we're storing to on the left, and the content that we want to write into that object on the right hand side. Okay, so now I'm going to create this object called favorite numbers, and I'm going to produce a vector that has a series of numbers in it. And we do that using this, it's just a simple C function. That C means concatenate, and that means connect or join together elements of various types. So here we're going to put in some numbers. I'm going to say 9, 18, 36, 0. So we have 1, 2, 3, 4 different numbers that are going to be concatenated together into a vector, and that vector is going to be stored in an object called favorite numbers. So if I type the name of the object, it's going to simply return the string vector values that are in that object. If I look at the structure of favorite numbers, it tells me that I've got numeric data. It's a vector with 4 elements, and it starts listing those values for me. Now we come back to this idea of set seed. So now we're going to create some random numbers. Again, simply because we can. And I'm going to produce an object called rand. And what I like is short, simple names of objects because they're easy to type. And they should have a name that allows you to figure out what's in them. And I don't need to write in random because I can type it in rand and it basically means the same thing in my head. It makes it a little bit easier to work with. So in this case here, we're going to now call a function called rnorm. And this simply means randomize from a random normal distribution, we're going to pull out values. And in this case here, we're going to draw 5 random numbers. So let's take a look at how this goes. Boom, it's done. And if I look at what it stores, here we have 5 numbers. They've been pulled from a random normal distribution. And if you set seed to be 100 on your computer, and you call the same function, you should have exactly the same 5 numbers that I have on my screen. Which, again, a little bit weird to think if they're random, how do we get the same numbers? But it's because we use the same seed. If we don't use the seed, then these values will all be different, and then it's often difficult for us to work through the examples and see if we're doing things exactly the same way, because you might get very different random numbers than what I got. All good so far? Okay, I'm just going to look back here. We keep adding objects into a workspace, so if I do a list again, I can see that they're all here. I have this object called rand that we just created. We have last name, first name, we have that vector of my favorite numbers, we have the grade that I got in the course, we have age numeric, and age as a character. These are all things that we created up here above. And we know that we can access any of these objects' values that they contain simply by typing them. So if I put in just the word grade, I get the value that it's stored. And if it's numeric, it means I can do math with grade. So I can say grade -3, and I can put any sort of string together mathematically and substitute numbers for objects that have numeric data in them, so that I can then have those variables contribute to the calculation. Of course, on this prompt, we don't have to necessarily use object numbers. We can do things like 4 plus 6. We can just use it as a calculator. We can do things like 8 times 7, plus 4. So we can use all of the operators that we know in mathematics to do calculations. But we can then take those calculations and we could actually store the result maybe into an object that we want to call, say, answer. And now 8 times 7 plus 4 is stored into this object. So the objects simply are containers that store the results of things that we do. Whether it's a mathematical operation or something else, we can store things as objects, and sometimes those objects are the final thing that we want, and sometimes they're an intermediate step, and they're things that we calculate to check things, and then later we delete them. And we can get rid of objects from our workspace. So maybe this is a good time to do that, because we know that capital A, age, is a character string, and it's not really useful to us. So maybe we want to remove this from our workspace. So we're going to use rm as the function. That's short for remove. And again, in the curved brackets, we're going to put in the name of the object that we want to get rid of. Be careful to use the capital A, age, and not the lowercase a, age, because otherwise we'll get rid of the numeric one. And again, we hit enter, and it doesn't ask you, are you sure you want to delete this? This is now sort of big kids. You either want to do it or you don't. Ask yourself, am I deleting the correct object before I hit enter? Because it's very easy to delete things or overwrite things and have things change. So again, ls, let's say we have this object called age. If I did this, it's simply going to overwrite that object, and it's not going to ask me, are you sure? Do you want to do this? It's simply going to do it. And it doesn't look like anything really happened, but now if you're expecting that object to contain the value 47, but now it contains 45, anything that you used that object for is going to be wrong. So if we look at age, sure enough, it simply has the 45 in it now. So keep in mind that as you do things, if you're not sure, write it to another object, something new, and then check, oh yeah, okay, that's great, then copy it over, then delete the one that you don't want. until you get comfortable doing this kind of work. Sometimes it can be a little bit daunting. But again, we can do a whole series of calculations using objects as the values, and those, I've got some examples in the PDF that I shared, and you can work through them. Multiplication, division, addition, subtraction, modulus, which is calculating the remainder after a division, all of those kinds of things, really, really simple to do. I'm not going to work through them all here today. I'm going to show you some things that are a little bit more fun. So we calculated earlier a list of random numbers that was 5 digits long. What if we wanted to pull out 1,000 random numbers? Boom, done. That didn't take very long. We have 1,000. Notice that in square brackets here we have 997. That means this object is the 997th one in our vector. This will be 998, 999, 1,000. So these numbers in square brackets along the side simply tell you where in the vector these first items on the row are, so that you can keep an eye or an idea about this massive number of data values. All right, but what's the use of having 1,000 random numbers on my screen when I could do something a little bit more interesting with that? And perhaps if I do this, what I'm going to do is I'm going to go to the insidemost brackets, and I'm going to resolve random normal drawing of 1,000 numbers, and then that's going to become the argument into the histogram function, or hist. And this is where R is really, really handy, because in one simple line call like that, we now have, and I know that my face is in the way, let me just slide that over. We have produced a histogram for 1,000 random numbers in a fraction of a second. And we can go in and we can start to change all of the ways that this is labeled and described, but notice that for a normal distribution, the middle value will be here centered on 0, and we'll have values into the positive and the negative range. And again, we're looking at here basically 3 standard deviations up or above and below the mean, and this really does embody what we expect for a random normal distribution from what we've learned in statistics classes. But we can use any series of values to create a histogram just by calling the hist function. In this case here, this was a quick way of getting lots of data by calling it for 1,000 random numbers. Again, we can do this in one step as I just did, or I could pull 1,000 numbers out of the distribution and store them into an object called nums. So if we look at what's in nums, we'll have all of our values. We can look at the structure. It tells us it's numeric values. We have a vector with 1,000 elements in it, and it lists the first few, and it says dot, 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 that there's a lot more, but it gives you an idea of what's in here. We can then simply call the histogram function for nums. And it's in behind my screen there, and there it is. But this is a new random distribution because I pulled 1,000 new numbers, so the distribution looks a little bit different. So again, it allows us to do this really, really quite simply and easily. Okay, I'm just going to slide this off to the side just so that we don't forget what it looks like. I'm going to provide a listing of our workspace again, just so that we don't forget what we have there. And let's go back and take a look at Fname. So this is a character, it's a vector with only one element in it, and it's character data, and it happens to contain my name. So we know that the length of fname is 1, because fname is a vector. Fname only has a single element in it. It's my name in quotation marks. How can we figure out how many characters are in my name? Well, this uses yet one other very simple function. Number of characters in fname. And you can see that it's 5. Like, oh, that's great, because now I can calculate what is the length of a character string that's stored as an element within this vector. And now this is a number. We can use that number and we could store it to a new object, or we can use it to do mathematics with. So if we wanted to use that 5 and say, well, let's multiply it by 50, we can take the number of characters of fname, which is 5, multiply it by 50, and there you go, we have 250. So anything that resolves to being numeric, whether it looks like a number, or it's the name of an object, or it is the length or the number of characters of that object, as long as it resolves to being numeric, you can use that result in a calculation. So that opens up a whole series of different types of options. Are we okay so far? Okay, so does anybody remember what the function for concatenation was called, for joining things together? It's crickets. It's so quiet. Yes, it's C. Thank you very much. Okay, so what if we did this? C, fname, lname. So it's going to put the two values from these objects together into one longer vector. And we're going to end up with a vector that now has two elements in it, my first name and my last name. But again, it's currently just showing it on the screen. We haven't stored it anywhere. So let's take that, but assign it to an object called names. So we have the result of concatenating my first name with my last name. We're going to assign it to a new object called names. And now if we look at the length of names, we should have 2, because there are 2 elements in this vector. But if we do the number of characters in names, we're going to have 2 results, because it's going to run this calculation on each element in our vector. So it runs the number of characters for the fname, which was 5, and it's going to run the number of characters for the lname, which in Ramel there are 6 characters. So we have a vector here with 2 results, 5 and 6. And of course, we can do all kinds of interesting things with these things. We could put the result of that into a function called sum and get the total number of characters in my name. So again, maybe not something that you're going to be doing for your research, but it allows you to say, well, if I've got this many objects in a vector, I can figure out how many elements there are. I can then calculate how long the text is, and you can pull those pieces out and mathematically store them or use them in future calculations. So there's all kinds of interesting things that we can do in that space that allows us to either work with the object names or to work with the data that's stored inside those objects. And this is the piece that we need to keep in mind when we're working in R, is that am I dealing with object names or am I dealing with the data within them? And is that data numeric? Is it character? Is it Boolean? Is it a vector? Is it a matrix? Is it a data frame? Is it a list? There's a whole series of different object types, and depending on what the object type is, you're going to be able to do certain types of operations with that data, and other things won't be possible. So it's really important to remember things such as the structure function that allows you to figure out what's in there. To use the is.character, the is.numeric, is.matrix functionality to find out what kind of data do I have. And when you know what kind of data you have, then you know, yes, I can do things of this type with it. All right. When we're creating data sets, there's a whole series of other tools that are really quite useful. One is called rep, and it's short for repeat or repetition, and we can do something like this. We provide the arguments 1, 5, and in this case here, it's going to produce a vector of 1 repeated 5 times. So if we need a vector, maybe these are plot identifiers or something like that, and say all of these observations are going to be taken at location 1, rather than typing in 1 multiple times, we can quickly repeat how many times that's to be calculated. So we can take that, and on the screen it's not as useful, but let's write it to an object, and I'm going to call this object A. So that now when I type in A, I get that vector of 5 ones. So I don't have to keep producing it. I have it there stored because I might need it for something at some point. The next thing that we might want to do is to, let's say, call the repeat function, and we're going to repeat 1 to 3 times, and we end up with a sequence that looks like this. 1, 2, 3, 1, 2, 3, 1, 2, 3. This 1:3 simply says starting at 1 and ending at 3. So it's a sequence of numbers from 1 to 3. We're going to repeat that sequence 3 different times. So that's also quite useful sometimes. So we're going to store this into a new object. I'm going to call it A2. So now if I look at A, and if I look at A2, they're stored as objects in my workspace. The other thing that might be of interest is to repeat a sequence of values, let's say 1 to 5, but we're going to repeat each one 3 times. So instead of taking the sequence 1 to 5 and repeating it 1 to 5, 1 to 5, 1 to 5, it's going to repeat each element in this sequence of 1 to 5 3 times. So we end up with 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5. And with these combinations, we can produce any sequence of these numbers to create sort of hierarchically nested sort of site numbers, sub-site numbers, and localized plot values, and start to create a matrix or a data frame into which we have sort of observations from, let's say, some field study. But it allows us to do this much more quickly than manually typing in a sequence of numbers and potentially making some sort of a mistake. I'm going to take this, I'm going to store it to A3 because that's what I do in my PDF output, because I might come back to it in some form or another. So those are repetitions. It's possible to also create sequences, and the function for a sequence is seq, and we might do something like this, where we create a sequence of values from 1 to 5. We can store this into an object. So obviously we're now getting into more objects, and now notice that we've wrapped our names of objects onto a second row. The second row starts with a 10, which means that this is now object 10, 11, 12, 13, 14. If you're not sure why this is a 10, we can start counting our objects. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then on the next row we start with 10. So So again, this simply tells us how many objects are being displayed on the screen. It helps us keep track of where we are. Sequence is also quite powerful because we can do things like this. And I'm going to write out the arguments with a little bit more detail now. We have an argument called from, and I'm going to start at 1 to 20 by 2. So we're going to create a sequence of numbers starting at 1, it's going to end at 20, and it's going to count by 2s. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, and obviously if we're counting by 2, starting at 1, we can't get 20, but we can't exceed 20, so the sequence ends at 19. So this is all relatively straightforward. That works really handily, but we can play around with, well, I'm going to save this too because we might need this. I'll store it as an object B2, but we can do things like the reverse. We can start from 20 and let's say count to 0, and we're going to count by -2. Oops, I overwrote the thing. See what I just did? I just overwrote, so I'm just going to go back and create that again. And I'm going to, instead of saving it as B2, I'm going to save it as B3. Oop, not B32. B2. And we're going to go from 20 to 0 by -2. So now if we look at B3, we have 20, 18, 16, 20, 16, 14, 20, all the way down to 0. So using rep or sequence, we can produce values pretty much in any order and sequence that we require for naming, numbering things. Really handy. This is much more challenging to do in Excel as things get to be a little bit larger and a little bit more complex. But in R, it's really easy to produce these sequences to label things, to keep track of things. Okay. So I'm just going to reorganize some things on my screen here. Okay. So remember that we have an object called A and an object called B. We can also take these vectors and we can perform operations on them. So we can do things like A plus B, and now by each unique element in those vectors, we can add them together. So we can do basically the 1 plus 1 gives us 2, 1 plus 2 gives us 3, 1 plus 3 gives us 4, and so on. And again, this is a really short vector, but if this was 100,000 units long, this function will perform that operation on every element of the vector, as long as they conform in terms of length. We can also test whether or not vectors are equal. So does vector A equal vector B? And then we get a result that is Boolean. And we see that the first element does agree. So this 1 in the first position of vector A, it's the same value as the first element of vector B. So true, A and B are equal at this location, but in all other locations within that vector, the values differ. So it's a quick way of testing, do my values match? Do they not match? If you're trying to check that you did something and you did it one way and you did another way and you're hoping that the results are always the same, you can quickly check. Is this vector the same as this vector? Well, if they're all true, then you're good to go. If they're not, then somewhere there might be a problem. So there's many ways by this could be used, but notice that when we're checking whether or not something is equal, it's a double equal sign. When we're doing double equal sign, things are going to resolve to being true or false. Not to be confused with the assignment statement, which is an arrow that says, write this stuff into a specific object. So we don't use equal signs when we're creating objects. We use equal signs and a double equal sign specifically when we want to test the equivalence of two things. And we can do this with yet another interesting operator. An exclamation mark equal sign is a not equal to. So it's saying, where are A and B not equal? So it's kind of thinking in the negative sense. And if I do that, notice that because A and B are equal, this resolves to false in the first position, but they are not equal in all of the other positions. We end up with true, 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 true. So we can control which way we ask the question that results in a Boolean result to force things to be true or false depending on what we need in which case. So again, it really is important that we know what data is in the object, what form is it in, what are we expecting those values to be, why are we testing them, which way are we testing them, and are we expecting true or false, so that we can then in our minds figure out what result we have and whether or not it's the correct one. So we can do things from all different sides, but we need to know that when we're testing equivalency, it's a double equal sign. A not equal is an exclamation mark equal sign, and assignment statements are this less than and hyphen sign that forms an arrow. So these are sort of key operators that you're going to find that you're using over and over again as you do things in R. And remember, if we have an object like we have here, this vector b, we can then calculate the length of b. Oops, I should probably spell things properly. And it tells us that there's 5 elements in that vector. So that works really quite well. If we look at A, we could also do something like calculate the number of characters in A, and it's, oh, they're all the same, they're all 1 character long, each location in that vector, but it doesn't have to be character data. It can very well be numeric data, and it tells you sort of what the size of that object within the vector actually is. So all kinds of interesting things that are going on in these tools. Remember we created this object called favorite numbers back in the beginning of today's class? So there it is, 9, 18, 36, 0. Well, what if we want to just extract some value or some values from here? We don't necessarily have to use all of them. So we can very easily do that too, but we can also perform mathematics as we did on any other numeric vector. So we might say 5 nums times 5, and we now multiply every element in that vector by 5. But what if we only want the 3rd element from here? To do that, we need to specify in square brackets the index of the value that we want to pull out or extract from this vector. And if it's the 3rd position, so this is the 1st, the 2nd, and the 3rd, this should give me 36. So I can choose which element to pull out of that sequence, and I can then do math with that result in the same way that I would with anything else. So sometimes we're dealing with the object. The object name is holding data, and we need to keep in mind, are we manipulating the name of the object or the contents? In this case here, 5 nums in square brackets 3 is extracting a numeric value out of that vector. Then with that numeric value, we can do math, in this case here, add 2 to it to get 38. So that works relatively quickly. If I go back to this, where we have favnums times 5, right, we can take this and write it to a new object. Let's call it favs. If I take take the third object of favs, I get 180. So sometimes I'm manipulating the values and then storing them to an object, and sometimes I'm extracting the values because I need to use them for some future calculation. It's possible to also say, well, I want to take all of the values from 1 to 3. So we use that colon sign to specify the from to, and now I'm extracting the first 3 values from this vector. So it's important to know what's in the vector, how long is it, where the values are, so that you can then specify the proper indices to extract the proper values out of it as you need them. Okay. Any questions so far? Is anybody working along with this, or is everybody just watching?
I have a question, but I mean, like, if someone else have questions.
No, go ahead. It's silent on here.
So, how do you remove the seed? When you set the seed to 100, how do you remove it? Because you have to remove it now, I guess, because it will be randomly created everything from 100, right?
Yeah, so there's a couple ways. One is if you restart R, it will just go back to the the state where the seed isn't set. Off the top of my head, I don't remember exactly, but you might be able to just call set seed with an empty set of brackets.
Oh, okay. Let's see.
I can't remember. No, I forget what it is. I'd have to look up on the help, but you can reset the seed. But if you just go in and set it to a new seed or restart your environment, it will reset it for you.
And okay. So the other question, I have a few questions.
Sure.
How do you remove object?
I did this one already with the RM.
Okay.
For remove. And you have to specify the name of the
Which
object
one?
that you want to remove.
Okay.
So, and again, you have to keep in mind that you spell it the same way with caps or no caps, because it will consider them as different objects if they're not exactly the same.
Okay, so one more I had. I think we did it actually. So if I want to specify how many characters there are in third element of my object.
Okay, so if we have an object that has multiple items, so let me just see, we have
objects.
We have names, right? I'm just going to create a longer set, and we can look at it, okay? So let's call this Marzana. Okay? So we have 3 different words.
Yep.
So if I type in this object called Marzana, and if I want to know the third element is ham, but I want to know the number of characters of the third element of Marzana, I have it there. Or, if I don't do that, I have the length of each of those elements in there. So egg has 3 characters, apple has 5, and ham has 3.
Okay.
Okay. So that The square brackets always allow you to drill in and identify an index for an element or a series of elements within, whether it's a vector, a matrix, or some other more complex data object. And then it brings those out for you. And then the question is, what do you want to do with them? Do you want to use those to do math? Do you want to do those to write them to the screen? Do you want to figure out how long they are? Do you want to multiply them all by 23? All of those things, the sequencing is always the same. You specify the object in square brackets, an extraction set of indices, and then that usually feeds into a new function or gets written to an object.
Yes. Can I ask more questions?
Sure.
Okay, so indexing starts with 1, or other cases when it starts with 0?
Yes. So in this case here, egg would be 1, apple would be 2, ham would be 3. And when it gets into more complex objects, which we probably don't get to today, but if you're looking at like a matrix, it's always going to be rows, then columns. So it's not sort of your classic X, Y coordinate system, it's matrix algebra notation. So it's always going to be rows, columns, or length.
All right, one last question. Is there a shortcut to write this arrow, the sign of less and then hyphen, because I'm always like...
You mean the assignment statement?
Yeah, the assignment statement.
No, not really. I mean, you could probably create something, but that's the interpreter. That's how R knows what you're doing. And it's intended to be visual so that you see it there, you know that it's not math, because the less than sign or the negative sign or that hyphen have meanings in math. But when they're stuck together like that, that never happens. So you know that when you see it, and I mean, I like to put spaces before and after all the operators just because it helps keep it clear. You don't have to. But when you see it like that, you know that, whatever's happening on the right-hand side is going to end up on the left-hand side. So it's a visual cue as much as it is a programming sort of standard.
Yeah, I just see you do it so fast, so I thought we had some short.
Yeah. Okay. Let me do a few more things, and then we'll see what time is it. It's so 10:50. Oh, time is flying. I didn't realize it was going to go so fast. I'm going to create nums1, and I'm going to create here a vector that has values 5, 23, 7, 8, 34, and 98. So when I type in nums1, there's my vector. I'm now going to create another vector, nums2, and it's going to be a vector with the value 6, 76, 12, 1, 0, and 24. And if I look at that, it's there. So the neat thing is that there are functions that we can now use, such as min, and we can put in nums1, nums2. So it's going to look for the minimum value across both of these input vectors. So we're going to give it both nums1 and nums2 and say what's the minimum value, and it's going to come up with the 0, which is the smallest value in those two vectors. So that's relatively handy. We can do that with with the maximum as well, and there's other ways that we can do those. But the neat thing is that there are functions that work with input of sort of single values, but if you provide it with a vector or with a matrix that have multiple values, it will simply perform that operation across all of those values that you give it. And if you wanted to, you could also not provide the entire vector. So you could say, well, let's just take the first 3 values from that vector, and let's take the last 4 values of nums1. And then when I run min, I get 6 because I've now omitted this 0. It was looking at the first 3 values from this vector and the last 4 values from that vector, and in that case 6 is the minimum. So we can subset vectors or matrices or arrays or data frames, complex data objects that we'll get to in future sort of workshops, but we can subset them however we want and then send the results of those subsettings into various function calls. I can create an object which I'm going to call a new, and it's going to be a vector of Boolean values, true and false in this case. And I'm going to create a new vector called bNew, and this is going to be false and false. If I look at a new and b new, we have vectors. Both vectors have 2 elements each, and they contain either true or false in them. So now we can do things like and or and XOR and all of the Boolean kinds of operators that allow you to pull out various combinations of conditions. So we could do something like this. A new or B new. And we see here that it says, well, if we're going to do or, it's going to resolve to be true if either or of the entries are true. So we say the first element of A new and B new, or in this case, resolves to be true because at least one of these is true. So we end up with true here. In the second case, in Boolean operator or, neither of these is true, so the result becomes false. So it's possible to use all of the Boolean operators, and if it's something that you're not familiar with, these are things that we could look at in more depth in a future workshop as well, but things like and, or, NAND, NOR, XOR, and NXOR, and there's all the combinations of Boolean operators. We could easily perform them using the true and false Boolean operators in R as well. So sometimes when you're trying to select subsets from your data, you want certain conditions but not other conditions, but sometimes these conditions or those conditions, but never those conditions. We can set up those Boolean queries to give us a string of trues and falses, and then use those trues and falses to extract values from another vector or another data set. So things just kind of get more and more complex in terms of the level of implementation, and I don't want to get into it today because it's going to be perhaps a little too muddy, but we can get to that in a future environment when we're trying to subset our data by various conditions. So if any of you have ever done SQL kind of work before, very similar concept where you choose your data set, you choose your conditions that you want to extract with. And my examples give a few of those in the PDF, and you can work through those if you'd like. I'm not going to go through all of them today. So I do realize it's 11, and we were scheduled to do this for an hour and a half. I'm going to leave it here. In the PDF, we're stopping just before the area where it starts with matrix operations. And when we do our next workshop, we can continue on from there. Feel free to take that PDF and work through the things that we've done and play with it, tinker with it. Feel free to work ahead, but we'll reconvene at some point when we have a chance, and we'll continue from here. If you have any questions, I'll stick around for a bit and I'll answer them here. But if you're working with it in the next couple days, couple weeks, and you have questions, you can always send them to me by Slack, and I'm more than happy to sort of help get you sort of sorted in R, because once you understand these sort of base functionality of how things work, and keep in mind what is an object and what's the contents of the object, and is it a vector or is it a matrix or is it Boolean data or integer data or character data, it becomes easier to think about what you can do with it. And half the time it's just grab a data set, say, well, now what I want to do is I want to figure out how to get the second element out of this data set. I want to try to get the third column out of this data set. I want to take all these values and multiply them by 5. And give yourself little tasks and see if you can get to do them. And when you can, write down how you did it so you don't forget. And when you run into troubles, ask me and I'll get you sorted out. Okay? So we'll call it the end of the workshop today, because I've got other things to get to as well, as I'm sure hopefully all of you do as well. But again, I'll stick around for a few minutes if anybody has any questions.